You got a dashboard full of charts, yet every meeting ends with the same debate. Which number is the right number? If you ever wrestled with definitions, sources, or data types, you're not alone. I'm here to help you learn the fundamentals of data concepts in Azure, from relational versus non-relational data to understanding transactional versus analytical workloads, so you can speak the language of data with confidence. Hello and welcome. We are glad you joined us. I'm Ilan Nyska, a Microsoft Technical Trainer with over 20 years of experience in the IT industry, specializing in Microsoft Azure architecture and cybersecurity. I translate complex technical concepts into clear, practical learning experiences that resonate with learners at every level. I'm here to walk you through the DP-900 course, Introduction to Microsoft Azure Data. This course covers 6 sessions where learners will build a foundational understanding of core data concepts and how data is stored, processed, analyzed, and then visualized in Microsoft Azure. We'll begin with Session 1 by getting an introduction to Microsoft Azure Data, core data concepts. Then we move into Session 2, where we will get an introduction to Microsoft Azure Data, relational data in Azure. We'll move to Session 3 with an introduction to data, non-relational data in Microsoft Azure. In Session 4, we'll go through Introduction to Data, analytics in Microsoft Azure. Next, we move to Session 5, where we will explore streaming and real-time analytics. Finally, in Session 6, we'll wrap up the course by exploring data visualization. Let's get started with Session 1. Welcome to explore fundamentals of data, designed to start the learning path of core data concepts and Azure data services, and build a solid foundation for future Azure data certifications. In this learning objective, you will build a quick foundation in core data concepts so you can recognize common data scenarios, roles, and identify the Azure services required. By the end of this learning objective, you will be able to identify common data formats and describe options for storing data in files and databases, distinguish between transactional and analytical data workloads, recognize common data professional roles, and identify Microsoft Cloud services used by those roles. We are focusing on what each service is used for, not how to set it up. This is about recognition, knowing which tool fits which data job. What is data? Data is a collection of facts, numbers, descriptions, and observations used to record information. We usually organize data around entities that matter to the organization, like customers, products, orders. Each entity has attributes, such as the customer's name, address, phone number. Data is central to everything an organization does. Organizations collect data, process it, and use it to produce outcomes. Imagine taking sales notes quickly during a busy day. You might write it down with extra details, use different formats, include information that feels useful at the time, but the data exists, but finding it will be hard, will take additional efforts. Now compare that to a predefined sales table. You already know which fields exist and what type of data belongs in each column. The structure makes it easier to store, search, and analyze. Not all the data is organized in the same way. Based on the structure, data is commonly classified as structured, semi-structured, and unstructured. This is an example of structured data. Structured data follows a defined schema, which means every record uses the same set of fields and data types. Because the structure is consistent, systems know exactly where each value belongs, making the data easier to store, search, and analyze. Semi-structured data has organization, but it allows variation between records. Data is commonly stored as name-value pairs, which means not every record is required to include the same attributes. For example, JavaScript, object notation, JSON for short, documents that store customer information might include different fields depending on what data is available. One customer record might include both an email address and a phone number, while another might include only an email address. Data is still labeled and organized, but the structure is flexible rather than fixed. This flexibility can reduce storage and also bandwidth requirements, but it's also meaning that you need to use additional logic to process the data. And structured data does not organize information into predefined fields or fixed schema. Instead, it is stored as files, such as documents, images, audio, video, and each file is treated as a single item. There's no requirement for those files to share a common structure. Even though a file might contain internal content or metadata, the platform doesn't organize that information into rows and columns. This makes unstructured data flexible and easy to store, but harder to query or analyze directly without additional processing. How data is stored? Broadly speaking, data is stored either in files or databases. Files are commonly used to store data outside of a database system. Delimited text is the simplest form. It stores data in plain text, where each field is a separate character like a comma, a tab, or even a fixed number of spaces. A comma-separated value file, known as CSV, is the most familiar example. Each line in the file represents a row, and the delimiter marks each column. It is easy for people and systems to read it, and it works well for structured data, things like product lists, customer records, or transaction log. Next is JavaScript object notation, JSON. JSON uses hierarchical structure made of objects and attributes, and those attributes can contain nested objects or collections. That flexibility makes JSON an add-on fit for situations where some records have additional details, optional fields, or varied shapes. You see JSON everywhere, from web applications templates for deploying resources to Azure to login systems, because it balances structure with flexibility. Extensible markup language, or XML, also uses text, but defines data with markup tags. Each tag describes what a piece of data it represents. XML used to be extremely common, especially before JSON became the standard for modern applications. You may still encounter XML in older systems or industry-specific integrations, but its usage has declined over the time. A binary large object, or blob, refers to binary files, things like Word documents, PDFs, images, videos, or application-specific formats. In blob storage, each blob is an independent object. This is usually stored as block blobs. And finally, we have optimized formats that were created to handle today's large-scale data workloads. Avro is one of them, a row-based format that stores a compact binary version of each record plus a small JSON header that describes the schema. Avro is efficient for storage and for transmitting data across the network. Then we have ORC, which stands for Optimized Row Columnar. Stores data in column stripes with built-in indexing and statistics. That design helps engines like Apache Hive read data quickly when running analytical queries. Parquet is another columnar format known for handling nested data types efficiently. It groups column data together and includes metadata so query engines can skip over chunks they don't need, which improves performance as datasets grow. Now that we have seen how data can live in files, the next question is how organizations manage data when it needs to be queried, related, and stored reliable over time. A database provides that centralized system. Let's start with relational databases. It is used to store and query structured data by organizing it into tables that represent entities such as customer, products, or sales orders. Each instance of an entity has a primary key that uniquely identifies it, and those keys are used in other tables for reference of the same entity. For instance, a customer primary key can be stored in a sales order to indicate which customer placed the order. This approach enables normalization, which reduces duplication by ensuring that details about a customer are stored in one place rather than being repeated on every order. These tables are managed and queried using structured query language, SQL. Non-relational databases take a different approach. Instead of enforcing a relational schema, they allow data to be stored in more flexible structures. A key value store consists of a unique key and an associated value. A document database stores its data as documents, so a unique key and a document. Those documents are typically in JSON format. In this model, fields inside the document remain visible to the database engine so they can query them efficiently. Column family databases group related columns together so that queries can read just the relevant families. And graph databases store data as nodes with relationships designed for scenarios where connections between things matter the most. These systems are often called NoSQL databases. Even though some of them support SQL-style querying, the set of formats and database types gives organizations the ability to store data in the way that fits its shape, size, and purpose. Operational data workloads support live business systems. These systems are optimized for online transactional processing, or OLTP for short. OLTP systems handle frequent read and write operations that represent real-time business activity. Updates are made transactionally. When an order is placed, that order is immediately recorded in the system. Each individual transaction represents a real business action and becomes part of the current operational state. Because these systems run the business, accuracy, reliability are critical. For example, let's say you sell a product. You don't want that product to still appear available after it has been purchased. Similarly, the customer doesn't want to pay for that again unless the transaction is valid and complete. To warranty this behavior, OLTP systems store data using transactions that follow ACID approach. Let's go with the first one. A, atomicity means each transaction is treated as a single unit of work. It either succeeds completely or fails completely. If a transaction includes multiple actions, all of them must be completed, or none of them will do. C, for consistency, ensures that a transaction moves the database from one valid state to another valid state. After a transaction is completed, the data must be accurately reflect the result of that business operation. And isolation ensures that current transactions do not interfere with one another. While the transaction is in progress, other transactions must see that consistent view of the data, not partial or mixed results. And finally, durability warrants this, that once a transaction is committed, it remains committed. Even if the system is shut down or fails, the committed changes are preserved. These characteristics make OLTP system well suited for operational workloads that require real-time accuracy, reliability, and consistency. Analytical data workloads. This is how data moves from operational systems into analytics without affecting day-to-day business transactions. Analytical data workloads are all about helping an organization understand what is happening in the business, not running the business in real time. Typically, they want to uncover trends over time, such as whether sales are increasing or decreasing month over month, how current revenue compares with previous quarters, or if customer activity is growing in specific regions. Performance comparisons are also key, for example, identifying which product sells best, which regions or teams outperform others, and how results this year stack up against last year. Instead of looking at individual transactions, they aggregate customer totals to see the bigger picture. They also search for patterns and behaviors like seasonal buying trends, peak usage times, or correlations. Analytical workloads are designed to deliver these types of insights, empowering organizations to make informed, data-driven decisions. These workloads support reporting, analysis, and decision-making, which means they are optimized for reading and interpreting data rather than capturing every transaction as it occurs. In a transactional system, such as an application backed by a relational databases, data is constantly being inserted, updated, or deleted through online transaction processing. Those systems prioritize fast writes and small, precise queries that serve day-to-day operations. For analytics, we don't take that path. It is a different approach because we don't want to slow down those live systems. The first step is to copy operational data out of those transactional environments using process called extract, transform, load, ETL for short. Extract means reading data from operational sources. Transform means cleaning it, reshaping it, and getting it ready for analysis. Load means storing prepared data in a dedicated analytical environment so that analysis can happen without affecting the performance of production systems. Second, after the data has been loaded, it's organized into a schema of tables designed for heavy, read-intensive queries. These tables might live in a Spark-based data lakehouse where SQL tables sit on top of files in a data lake, or in a traditional data warehouse that uses fully relational SQL engine. The goal is to structure the data so analytical queries over large volumes of information run quickly and efficiently. A data lake stores large volumes of raw data in files, and in Azure, this is typically implemented using Azure Data Lake Storage Gen 2. A data warehouse stores structured data in relational tables, and Azure provides services such as Azure Synapse Analytics and Microsoft Fabric Warehouse for that purpose. A data lakehouse combines the flexibility of a lake with the tabular structure of a warehouse. And in Azure, this can be implemented using Microsoft Fabric Lakehouse or Azure Databricks Lakehouse. Third, once the data is organized, it might be aggregated into an online analytical processing model, sometimes referred to as a queue. Unlike a relational table, which is limited to rows and columns, these models organize data across multiple dimensions, and they pre-compute common calculations such as totals of comparisons so that the results are immediately available without recalculating each time. Finally, analysts and business users query the data to produce reports and dashboards. These tools make it easy to identify trends, compare performance, and support informed decisions across the organization. The key idea is that analytical workloads are optimized for reading and understanding data at a scale, not for recording individual transactions. They provide the insight layer that helps organizations turn raw information into meaningful business intelligence. Let's do a quick knowledge check to reinforce the key concepts we just covered. How is data in a relational table organized? Think about it. First, a relational table is organized into rows and columns. Each row represents a record, and each column represents an attribute of that record. Which of the following is an example of unstructured data? Unstructured data does not follow a fixed schema. Audio and video files are good examples because they don't have a defined row and column. What is the data warehouse? Finally, a data warehouse is a relational database that is optimized for read operations. It is designed to support analytical queries, reporting, and dashboards rather than frequent transactional updates. Now that we covered core concepts, let's look at the people and services involved in working with data. When systems get bigger, one person doing everything doesn't scale. This separation of concerns helps keep data environments reliable, secure, and easier to manage. Here are some of the most common data professional roles that you will encounter. No need to memorize job titles, but it's just to understand who is responsible for what in a data solution. First, the database administrator, often called DBA. The database administrator is responsible for keeping databases reliable, secure, and available. This includes provisioning databases, managing access and security, performing backups and recovery, and monitoring performance. DBAs focus heavily on operational and relational database systems, making sure they are protected and running efficiently. Next, data engineer. Data engineer focus on moving and preparing data so it can be used for analytics. They build data pipelines, manage, extract, transform, and load, and ensure data arrives in the right place, the right format, at the right time. If you think back to the analytical data workloads we discussed earlier, data engineers are often responsible for getting data into data lakes, lakehouses, or data warehouse. Then there's the data analysts. Data analysts work with prepared data. They build analytical models, create reports and dashboards, and produce summaries and visualizations that help the business understand what the data is telling them. Data analysts are typically focused on answering business questions, identifying trends, and supporting decision-making rather than managing infrastructure. It is important to note that in real organizations, these roles often overlap. In smaller teams, a single person might act as both data engineer and data analyst, or even take on some of the database administration as well. As data solutions grow, each role tends to become deeper and more specialized, and each require focused skills. Larger organizations usually separate these responsibilities because the depth and complexity of each role increases as the environment scales. You might also encounter related roles such as data scientists who focus on advanced analytics and machine learning, or data architects who design the overall data platform and structure. The key takeaway is recognizing the core responsibilities of each. Here's a high level of Microsoft services most used for working with data. You don't need to remember all of those. We will list the most important ones. And this is not all of what you have. This is not exhaustive. We'll explore several of these services later in the course, once this foundation is in place. On the operations side, Azure SQL represents structured query language family of relational databases options that includes Azure SQL Database, a fully managed platform as a service offering hosted in Azure. Azure SQL managed instance, also platform as a service offering that is more compatible with SQL than Azure SQL database is, but less flexible and comes with additional administrative responsibility. Azure SQL Virtual Machine provides full customization and you assume full responsibility for its management. Azure Database for open source engines offers MariaDB, MySQL, and PostgreSQL. Azure Cosmos DB is a born in the cloud, highly scalable, non-relational database system. And Azure Storage supports file, blobs, and table storage, including hierarchical namespace used for data lake storage. On the analytics side, some services combine several capabilities to support end-to-end insights. Services are grouped by their primary workload, even though modern platforms might span multiple stages of the data lifecycle. Microsoft Fabric brings together everything an organization needs for analytics in one software as a service experience. It supports data ingestion and extract, transform, load pipelines, lakehouse and warehouse storage, data science, and machine learning, real-time analytics, visualization, and governance. It includes elements similar to the pipeline tools found Azure Data Factory. A SQL Server-based relational warehouse engine and a Spark environment similar to Azure Databricks. Spark itself is an Apache open source technology designed to process large volumes of data in parallel using language like Scala and Python. Azure Databricks provides the Spark environment as a platform as a service option, and Microsoft Purview helps organizations build a map of their data, follow lineage across systems, and apply governance consistently. These services are shown together here so you can begin to recognize where they fit within the broader data landscape. We will revisit several of them later on the course once this high-level picture is in place. Take a moment to think through each question. The first item asks, which one of the following tasks is the responsibility of a database administrator? This is meant to reinforce that the administrator is responsible for core operations such as backing up and restoring databases. The second question is, which role is most likely to use Azure Data Factory to define a data pipeline or ETL process? The second question focuses on Azure Data Factory and highlights the defining extract, transform, load pipelines is part of a data engineer work. The final question is about which services will you use as a software as a service solution for data analytics. The final question is about recognizing a software as a service analytics solution, which points to Microsoft Fabric. These quick checks are simply a way to anchor the roles and services we introduce and make sure these distinctions between them are clear. In session 1, we focused on core data fundamentals. We introduced what data is, common data formats, and how data is stored in files and in databases. The session explained transactional versus analytical workloads, outlined common data professional roles, and provided a high-level overview of Microsoft Azure Data Services, with an emphasis on recognizing when to use each service rather than how to configure them. With this foundation in place, we're better prepared to take our next step on our journey. This concludes our session. We hope you join us as you move through this journey learning with us. We encourage you to watch our videos in this course or search out your next favorite topic on Microsoft Learn at aka.ms/learn.